Let's look at exponential growth and decay. First, we'll actually check out constant growth and what it looks like. So y equals 2x. There's an xy chart. If you plug in values for x, 0, 1, 2, 3, and 4, you simply multiply them by 2 and you get those answers for y. And if you graph it, it's a nice straight line with a slope of 2. Every time x changes by 1, y changes by 2. But that's not how exponential growth works. If we have y equals 2 to the x power, so now the variable is in the exponent position, we make this xy chart and the y values go up in a hurry. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, and then it really starts to jump. 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is 32. And so this graph is not a straight line. It really curves and it really accelerates, goes up very quickly to the point we can't even see where we have the x value of 4 and the y value of 16. Here's a graph of 1.45 to the x power. It also curves and goes up quickly. I'll go backwards. It's not quite as steep as 2 to the x power. Flattens a little bit. And flat growth is when you have 1 to the x power. 1 to any power is 1, so you get this straight line here. So when this value is greater than 1, we get an upward curve. Here's 1.45 to the x power. Here's 2 to the x power. And then when we hit 1, it's totally flat. So let's look at an example of exponential growth. You've got a house that's worth $100,000 a year and you're expecting it to go up in value. We'll use the word appreciate for that. When something is appreciating in value, it's going up in value. And we're expecting it to appreciate at a rate of 10% per year. What will be the value of this house in 5 years if that's what happens? One thing we can do is make a chart that's kind of slow, but it will show what's going on. At year 0, it's like having a stopwatch starting at 0, the value of the house is $100,000. But it's going to go up by 10% every year. That's the decimal 1.10, because if it went up by nothing every year, that would still be keeping its value at 100%. And 100% as a decimal is 1.00. But we're going to go up by 10%, so we're going to multiply by 1.10. And when we do that, after 1 year, the value of the house has jumped to $110,000. And again, you can see the 10% increase here. 10% of 100,000 is 10,000, and that's how much the house has gone up. In year 2, we'll multiply what we had before by another 1.10, and the value goes up to $121,000. In year 3, we have to again multiply by 1.10, and we fill in the chart and find the value of the house is $161,051. That took a little bit of time. It wasn't so bad for 5 years, but if we had to do that for 20 years, that's a lot of chart filling in. Hopefully, there's a faster way. There is. Notice this pattern that we have the starting amount, which we're going to call principal, is in every one of these formulas, and we multiplied here by 1.10 one time in year 1, 2 times in year 2, 3 times in year 3. You see the pattern. So here's our exponential growth formula. And here's what everything means. P is our initial amount, which in our problem was 100,000. The rate of change, remember to turn that into a decimal. So if it was 5%, it would be 0.05, and we'll add it to 1 because things are going up. Time is in the exponent spot because that's how many times we had to keep multiplying by that number. And then A is the amount we have at any given time. Let's apply this to the example we just had. So the house is worth $100,000. It's going to appreciate in value at a rate of 10% per year. What will its value be in 5 years? Well, there's several things we know and one thing we don't. And you can go in any order. I'll start with the time. Time is 5. It says so in the problem right here, so I'll make t 5. The rate of change is 10%. As a decimal, that's 0.10. The starting amount, the initial amount, P, principal, was $100,000. So that's going to go in the P spot. And the amount we have at this time in 5 years, I don't know what that is. That's what we want to find out. So now we can take all these values and fill them in. I'll go back so you can see, and then they go in. We want to take care of the things in parentheses here to get the rate first, then we can use the exponent. Do that before we multiply. Don't multiply by 100,000 now. Follow the order of operations. Well, the 1 plus 0.10 is that 1.10 we came up with earlier. And we're going to take it to the 5th power. That is 1.61051. Sorry for the crazy colors here. And then we'll multiply that now to 100,000 and get 161,051. Well, that's the answer to our problem. And it wouldn't have been any harder to do that if we were trying to do 25 years instead of 5 years. So it was much faster than making a chart. But the chart explains why it works. That's why we can use that exponent, because we have to multiply by that rate every time for that many years. Well, you try this one. A website has 500,000 members and expects to increase its membership by 15% every year. So how many members will there be after 6 years? Please pause the video and give it a try. Here are the values that we get from the problem. There's 500,000 members at the start. That's going to be P. The rate of change is 15%, 0.15, and the time is 6 years, so T will be 6. We pop those in. We'll get 1.15 when we add the 0.15 to the 1. That 1.15 to the 6th power is 2.313060765, and then multiply to the 500,000, and we're going to round to the nearest person. We're not going to have decimals or fractions of people. We'll round to the nearest person. So they'll expect to have 1,156,530 members after 6 years. Exponential growth can be both good and bad. It depends what the situation is. If you've got something that's going up in value, like a antique or a house or something like that, you'd be excited about exponential growth driving the value up. But exponential growth can be bad for something like a virus. If one person gives a virus to 2 people and those 2 people give it to another 2 people and they give it to another 2 people, as we saw before, the numbers go up very quickly. So exponential growth could be good or it could be bad. We've also got exponential decay. So instead of things going up in value, they're going down in value. And you notice the difference here is the minus sign. Everything else is the same. So the A, P, R, and T all represent the same things. If you didn't pause the video earlier to write these things down for exponential growth, you might want to do it now for exponential decay. Same thing, except there's a minus sign here instead of a plus. So let's look at this example. We've got a brand new $48,000 sailboat, but it's expected to depreciate in value at a rate of 30% per year, because we're going to be using the boat. It's going to probably start falling apart. What will the value be in 9 years? Well, let's start filling in what we know. And you can go in any order. We know the time is 9 years. It says so in the problem. T is 9. The rate of change is 30% per year. That's how much it's going to go down. And the initial amount for the sailboat was $48,000. And the amount we have after 9 years, don't know what it is. After 9 years at that time, that's what we want to find out. So we'll plug those values in. And then we'll subtract 1 minus 0.30 and get 0.70. And that makes sense. If you think about it, if you lose 30% of your value, at least you get to keep 70% of your value. It's just a different way of looking at it. Then we'll take care of the exponent. And then finally multiply times the 48,000. And this boat has really dropped in value after 9 years. We'll round to the nearest cent. So the value of the boat after 9 years is just $1,936.97. Often heard that the 2 best days of boat ownership are the day you buy the boat and the day you sell the boat. Exponential decay can be good or bad. In this case, exponential decay was kind of bad because you spent a lot of money at first for the boat and then it went down in value. That might hurt you when you want to sell it later. But if you're into used vehicles, exponential decay can be a good thing. If you have a medical condition and maybe you need to get a shot, then there's probably exponential decay for whatever the drug is that put into your body. If doctors can determine how long that's going to take before you drop to another level before you need another shot, at least they can use exponential decay to help them out. It Could also be a case where you have a drug you don't want to have in your body. Maybe somebody you know is going to get a drug test and they want to know how long it's going to take for the decay of that drug to leave their body so they could pass a drug test. If you have a radioactive element, maybe you want to know how long it's going to take for it to get halfway to radioactive, something called its half-life. Maybe it'll be safer to deal with it at that time. Generally, machines and things that get used experience exponential decay because they're going to go down in value.